bucket moves upward with a constant speed. A. How much work is done by gravity in the ascent? And B. How much work is done by the boy in the ascent? Somebody tell me that. It's cool.
Hey, Sean? Visitor? All right. So we're looking at number 9.
What happened? Oh.
Okay. So what did they say on number 9, as Eleuterio read for us? What are we trying to calculate in part A?
How much work is done by gravity?
Work done by gravity, and that's an important distinction. Work done by gravity. So the challenge in this problem is really choosing your angle. So for 9A, we're looking at work done by gravity. Part A is work done by gravity. Take a quick look at part B. It's work done by what?
The boy.
The boy. Okay, so the challenge in this problem is pretty much figuring out theta. So theta is the angle between force and distance. What direction does gravity pull? What direction is the force of gravity?
Down.
Down, of course. So that's force G, force of gravity. And in this problem, maybe you could take another read. Can you figure out what direction the bucket is going? Is the bucket going up or down? Up. It's raising it from the bottom of the well all the way to the top. So the distance is up. Gravity's down, distance is up. What's the angle between the force and the distance?
Zero.
Not in this case, not 0.
1.
Let me make sure I'm thinking. 180. Since they're opposite directions, angle is 180. We'll see in a second the work done by the boy will have an angle of 0 degrees. And now we're just talking about the angle. We'll actually get to the calculation in a second, but again, the bucket is being risen up. What direction does the boy pull? What direction is the force of the boy? He's pulling it up the well. So force of boy, sometimes we call that applied force, is up. But still, what direction is the bucket going? Up. With these arrows in the same direction, we have an angle of 0 degrees. So in part A and part B, we have a 180 degree angle and we have a 0 degree angle. This is the crux of the problem, figuring out which of those is 0 and which of those is 180. On the test, we'll have the same thing. Something either going up or going down, and two different things doing work. Work done by gravity has a 180 degree angle, work done by the boy has a 0 degree angle. If the thing was descending, if he was bringing the bucket downwards, the angles would be reversed. If it was going down, well, let's look at that. If it were going down, this would be flipped. Distance would be down. So what's our angle there?
1.
Why is our angle 0 here? Same direction. Cycles here like every day. That's good though. Poor Emily. Okay, so let's actually solve the thing. We're going to find a little bit of a hiccup. Okay, theta's 180. Distance, how tall is that well? I think it was 12. 12? Maybe I'm making stuff up. 12 meters, that's a lot. But they did not give us the force. To figure out force of gravity, we have to do something else.
Mass times gravity.
Mass times gravity. So I don't really have a good spot for this. I'm going to open up a new page. You should probably do yours off to the side or something. Oh, JK, I'm not going to open a new page. I'll just do it down here and I'll erase it. So force of gravity is going to be m times g. Mass of the bucket was 9.4. Cool. 9.4 times 9.8, and we'll get 92.12 newtons. So that's the gravitational force. And since it's gravitational force, that's what we're using here. Like they want the work done by gravity. They want the work done by gravity, so we have to use the force that gravity is using. Gravity's pulling with 92 newtons of force, so we use that number to figure out the work done. Times cosine 180 times 12. Wait, what? The 180 messing us up? 92.12 times cosine of 180 times 12. Kind of messy, but. What you get?
Negative 1,105.
All right, negative 1,105 joules. 1,105 joules. Questions there? Part A? This is the work done by, what is this the work done by?
Gravity.
Gravity. Okay. We're ready for part B. Now gravity pulls down with 92.12 newtons of force. Guess what? The boy is pulling up with 92.12 newtons of force. How do I know that? How do I know that gravity's pulling down with the same amount of force as the boy is pulling up? How do we know?
Constant speed.
Constant speed. That's it. If it's rising or descending with a constant speed, the forces are going to be the same. The vertical forces are the same, pulling up and pulling down with the same amount. That's times cosine 0 times 12. So for those of you that are fantastic at geometry, you know that they're going to be the same number, but one will be positive. Fortunately, we don't have to memorize that. You can just type it in your calculator. So basically, gravity's pulling down. It's trying to speed up this bucket so that it just flies down and hits the ground. But the boy is pulling up, and he's keeping it at that steady pace. So since they're using the same amount of energy, it keeps it locked in at that constant speed. If one were larger, it would start to accelerate. So the gist here is, to figure out your angle, you got to draw those. That's the main thing I'm trying to test you on in this problem. To figure out your angle, you have to draw the force doing work and the distance that the object moves. All right. How do we feel?
It's hard.
It is tough, yeah. Physics ain't easy. If it were easy though, it wouldn't be fun. That's what I was saying.
I think a lot.
Okay. To prevent him from, we should give this puppy a name. What are we gonna call him?
Yes.
Alberto.
Alberto. I like it. Or what? Biscuit? It'll be Alberto Biscuit. What's his last name? McGuire, that's fine. Alberto Biscuit McGuire. I'm going to call him Biscuit. So, to prevent Biscuit from examining a nasty smell too closely, Jen pulls on the 22 kilogram pup with a force of 50 newtons. The force is directed at an angle of 40 degrees, and the pup moves with a horizontal distance of 1.15 meters. A. Calculate the work done by, what do you see there? Very important, work done by gravity. Then part B, calculate the work done by Jen. So The difference in this problem is the work done by a certain person, and that changes everything. So let's look at A. Trying to get work, which is this equation. Okay. Force. Now, there are a lot of forces in this problem. We've got the person pulling, that's the applied force. We have gravity that's pulling down on the dog. We have the dog pushing itself forward. Probably a little friction from the dog sliding, but why are we going to use gravitational force for F? Work done by gravity. If it says work done by gravity, we're concerned with the force of gravity. So we would take, in order to get that, we would take m times g, but there's actually a little shortcut in this problem. You could do that, you'd still get the right answer. You'd take 22 times 9.8, and you'd plug it in there. Distance, I think it goes 1.15 meters. Yep, there it is, 1.15 meters. And let's look at theta. To get theta, we have to draw force, we have to draw distance. So, what direction is the force in this problem? Down. Work done by gravity, well, gravitational force is down. The dog goes a distance horizontally. So what's our angle? 90. If you plug all that in, you're going to get 0. So you could plug in force, whatever that is, 22 times 9.8 times cosine 90 times 1.15. But if you know that this equals 0, you can just show this. So the minimum amount of work that you need in this problem is just writing cosine 90. And that's how you know work is 0 joules. Gravity's pulling down, the dog is moving sideways, and that means gravity's not doing anything. Gravity's not changing anything. Only when the dog rises up or down could gravity have a non-zero work. And then part B is pretty simple. Part B is the work done by Jen. Is she pulling horizontally, vertically, or at an angle? Angle. There's her force. Force of person, or force of Jen. Distance is sideways. And the angle that they gave us is this right here. This little angle in between, 40 degrees. So, pretty easy problem. You don't really have to show the picture for this one if you know what's going on. I think she pulls with 50. I think the angle's 40. I've got to double check myself. But that's it. 50 times cosine 40 times 1.15. Yeah, that's it. I got 44. So, there's going to be a problem like this. Someone's pulling at an angle, or something pulling at an angle. You have to figure out the work done by gravity and the work done by the person. If something's moving sideways, like, so on this problem on the test, someone's pulling at an angle, the work done by gravity is 0. It's 0 on the test, it's 0 on number, whatever next one is, number 12, work done by gravity 0, and the one on the test would be the same. How's it going? Yeah, cool. Swallow so far. Questions there before we go to 13? All right. 13. Oh man, we're almost done. Cool. 15, 16, 17 take like 5 seconds, so we'll be good. We'll have plenty of time to work. I'm tired of talking. Anybody want to read? You guys want to read? If anyone else wants to go, they can take his spot because he already went. Sorry, Altair, Chris wants to go too.
An elevator brings a group of people totaling to 620 kilograms upwards of the third floor, which is 9 meters off the ground. Calculate the power generated by the elevator if this trip takes 14 seconds.
All right, thank you. Let's look at power. They asked us to calculate power, so let's start with our power equation. Kind of jump the gun there. They asked us for power. What else did they tell us? They say 620 kilograms is mass. What about that 9 meters? What would that be? Distance. And they gave us one more thing. What do you see? Time. So we have mass, distance, time. I want you guys to choose. Which one do you like? Do you like izquierda or derecho? Which one do we like? Izquierda. Why do we like this one? Why do you like that one? Time. We already have time, so it's a good way to go. We just need to figure out work somehow. And then that one's useful. So this is 14. Let's see if we can figure out work.
So work would be 180.
Work would be what?
Cosine would be 180.
Let's see. Cosine. Let's look. Let's figure out our theta. Well, let's go left to right. So force. Yeah, we take mass times gravity, but they want power. Do they want the power generated by gravity or the power generated by the elevator? So you guys are saying, okay, this is the work done by the elevator, but you guys are saying that force is mg. You guys are right. You guys are right. Why is the up force the same as the down force? Constant speed. They didn't say that in there. On the test, I would definitely say that. So since it's a constant speed, yeah, force of the elevator is the same as the force of the gravity. So yeah, we can use that. So it'll be 620 times 9.8. I think it was 6076. Cool beans. So, just in case you missed that, force of gravity is 6,076. Force of the elevator, also 6,076. Those two are the same because we're rising at a constant speed. Elevators rise at a constant speed. Okay, so we're halfway there on this one. Not halfway, I guess. But yeah. 6,076. We don't know our angle yet. Is distance in there? Yeah, 9. Yeah, so we have to decide our angle. And in order to do that, we have to look at our forces. Let's see. First of all, the two questions we have to ask are, what direction is the elevator pulling, and what direction are the people going? Up for the elevator pull. Where are they going? Up. So they're both pointing up. Just like we drew in the last problem. We have force is up. Force elevator is up. Distance is also up. So there's our 0 degree angle. So 0 degrees. And little side note, if I ask you for power, it's going to be a 0 degree angle. So that's another way to remember it. too tricky. This number is very large. 54684. 54684. Let's figure out if that's our final answer. What is the problem asking for again? Power, okay. We have work. We're actually looking for power. So we'll plug that back in up there. Power is work over time, so we'll divide this by 14. 54684.
Me too.
And our unit is watts. Kind of confusing. Unit for power is watts. Unit for work is joules. So for this problem on the test, I'll ask you the power generated by, let me make sure, I think it's always something, no, not really. Yes.
So, like, when we're asking a question, is it gonna be like this? We see how it's like broken into pieces, or is it gonna be all combined stuff?
It'll be all combined, so I won't have the bold print. Oh, Jesus.
That's what helps me.
I'm done.
Does? Why does that? So out of curiosity, why does it help? Because you see the equation there?
No, not the equation, but you see, like, it's telling me reach its max height and stuff. Like, you see what I'm saying?
Yeah.
That helps me. Okay.
But that's always stuff I'll point out to you. Like, you don't know where to go, I'll say, so figure out how long to reach max height or something like that. So I can give you little clues like that. But if you ask me, my least favorite question during a test is, which equation do I use?
Oh, no.
That's the whole class. So
I understand that. It just, I don't know, like, how to start it off.
okay, I can always give you hints. So don't let yourself leave stuff blank.
I just don't know.
You.
All right, I'm trying to figure out which is going to be more annoying. So 15, 16, 17, they go from hardest to easiest. Should we start on the easiest, number 17? Okay. Appreciate the feedback. Let's start with 15 then. I'm going to do 15, 16, and 17 for you. This is what the extra credit problem will look like. It'll be something like this. Yeah, okay. So prove that 1 watt is 1 kilogram meter squared per second cubed.
Oh, yeah.
And here's where you start. It's really easy, actually. What does watt measure?
Power.
Power. So you start with that. Power equals work over time, or power equals force times velocity. You can start with either one of those. And what you do is you plug in units. Kind of hard to explain. Okay, let's look at it this way. Okay, time is in seconds. You know that. Time is in seconds. What's work measured in? Joules. If I were to plug in my units right now, it would be joules per second. That doesn't prove anything. We want our answer to have kilograms meters squared per seconds cubed. So I'll show you the easier way. In my opinion, this is the way to go. What's our velocity? What is velocity measured in? Meters per second. Force is newtons. So here's what we're going to do. F equals ma. So I can plug this in. It's only like, actually that's the second to last step. F equals ma, so I can replace F with ma. We'll plug in our units right now and we're done. So let's do these units one by one. Units for mass, kg, kilograms. Units for acceleration, meters per second squared. And for velocity, meters per second. Bam, there's our answer. Kilograms times meters squared. These become squared. Time divided by seconds cubed. Divided by seconds cubed. So, power is kilogram meter squared per second cubed. That will take you. That will take you 5 minutes to memorize,
5 minutes.
and you'll get your 2 extra credit points on that test if it appears. I'll probably put 2 of these. Sorry?
We're gonna show that.
All this right here, yeah, that's 2 points.
I need all extra credit points.
Amen.
So again, I don't know how to ask this. I don't know how to quiz you here.
Just
I
say,
replaced F with MA. What is that? What is the equation altogether? Kinda. Yeah, F equals MA, so we replace that. Yeah, that's pretty much it. Okay. Let's just try another one. That'll be the best way to practice. Prove that 1 joule is 1 kilogram meter squared per second squared. And here's where you start. The 15, 16, and 17. You start by asking, what is that left unit measured in? So what is joules? What does joules measure? Work. Joules measures work. This one's a little bit, you know what, this one is a little tougher in my opinion. Now, what did we replace F with before? MA, very good. So we'll have work equals MA cosine theta times distance. Yes?
So when do you know when to use MG and MA?
You could use MG here as well. Either one would work. Because the units for A are meters per second squared. Units for G are meters per second squared. Do you mean like with the math problems though? Because there's something to say there too. No? Okay. For here it doesn't matter. So we'll plug in our units. Work is kilograms. Acceleration was meters per second squared. Unit for cosine is, well, there is no unit. Cosine theta has no unit. You can plug in cosine theta, or you can plug in, I mean, it really should just disappear. So we would have 1, or you can just leave it out. Yeah, what's our last one? Meters. So there are a bunch of other ways to do this problem. I'm going to show you the easiest one if there's our 1 proof. In my opinion, for 16, there's an easier way. Krista, question?
Why does the cosine cancel?
Cosine has no unit, so I think the proper way to write it would be like this. 1 meter. So cosine theta has no unit. There's an easier way to do this. If you're one of those people out there memorizing, unit for work is joules. Unit for energy is also joules. So to prove here that 1 joule is that, we can use this. In my opinion, this is way easier. Because there's nothing to plug in. That's kilograms. What's G? Unit for G. Meters per second squared. And height is meters. Bam, that's it. There's our proof.
Hey, Mr. McGuire,
What's up?
like, what is this called? Like, I ain't trying to be funny. Like, is this, like, I know it's physics, but like, it's like a topic.
This right here with the units, I think it's called dimensional analysis. But I'm not sure. I think, did you guys, I don't know. Your chemistry teachers would know because it's like, You guys do something like this in chemistry. I'm gonna look that up because I actually don't know what it's called. Okay, last one. 1 Newton. Oh, there's actually a typo here on the paper. Yes.
So would this be FG equals mg since we're measuring it by force?
Yes. So Tia pointed out this is measured in newtons, so we can use this as a proof.
Good job.
We'll have kilograms, meters per second squared. So the paper is actually a typo.
Okay.
This is the real answer. This is the real answer for number 17. It should say 1 Newton is this. Now some of you might not approach it as Tia did. You might go like this. You might say F equals MA. Same thing. Kilograms, meter per second squared. Kilogram meter per second squared. I like this stuff. It's clean. But here's the cool part. So everything we've studied so far, we have energy, work, power, forces, speed, time. All of those things are measured with these 3 things: kilograms, meters, seconds. So everything that we perceive apart from electricity can be summarized like this. We have matter, we have space, and we have time. So everything, not in the universe, but much of our universe can be described by an interaction between matter, time, and space. But you don't need to know that. There's just something there. There's something there that I can't quite grasp, but it's pretty cool. What questions we have? Because you don't need to know that. That's just cool stuff. But if you do want to know that, there it is. Time and space. Some people say that time and space are the same thing. But I don't want to give you nightmares. We won't talk about that. So the last 3 to do here are these guys. Pretty sure these are correct. I'm not certain, but I'm pretty sure they are. Let me know if you get the same answers. And when you're done, show me what you got. You should have 1 through 8, and if you have those, I'll look at them. And then 9 through 17, I'll check in separately. So if you finished either of those sets, show me before you go. You got 20 minutes. 20 minutes, yes. Take the pad.